Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. In this video, I want to talk about a couple of examples related to stochastic processes and see how we can use everything that we learned in previous video to model these systems as stochastic systems, more specifically as Markov chains. So just to review, for any problem that we get and we want to model as a stochastic system, we first have to read the problem statement carefully. Then we have to find out the characteristics of interest that we want to monitor. In other words, we have to find out what is forming the state of the system. Then we have to find out the state space or the set of all possible values that the state variable can get. Then we have to form or put together the transition probability matrix P. And finally, if the data is available, we have to find the initial probability distribution vector Q. Okay, in previous video, we talked about all these steps and what do they mean. And now we're going to go through a couple of examples so that you get a better sense as how these steps are used. In the first example, we are looking at the town and the weather condition of the town. 90% of all sunny days are followed by sunny days, and 80% of all cloudy days are followed by cloudy days. We want to use this information to be able to model the weather condition in this system as a Markov chain. So obviously, the first step, read the problem carefully. The second step, find out the characteristic of interest that you want to monitor, and that is going to be the state of the system. So here, obviously, the weather condition is the state of the system. So what we want to monitor is weather condition. Okay, then find out the possible values that the state variable can get. In other words, find out your state space. Okay, so what are the possible values that the weather condition can get in this problem? If you read the problem carefully, you will see that there are two possible values for weather condition: sunny and cloudy. Okay. Next, we have to put the transition probability matrix together. So as we said before, when we want to put the transition probability matrix together, the number of rows and the number of columns in this matrix will be equal to number of possible values for the state of the system. So here we have two possible values for the state of the system, sunny and cloudy. So we will have two rows, one for sunny, one for cloudy, and two columns, one for sunny and one for cloudy. Okay, so now we are going to fill this transition probability matrix. So this element is going to show the probability that if we are at the sunny day right now, what is the probability that we end up at the sunny day in the next day? So as we see in the problem statement, 90% of the problems of the days that are sunny will be followed by a sunny day. So this would be 0.9. So then what is the value that we have to put for the next element? So obviously we don't have in the problem statement that, if we are in sunny, then what is the probability that the next day is cloudy? However, we know that the sum of the probabilities of each row equals to 1. So if the probability of the first element is equals to 0.9, then the probability of the second element should be 0.1, because the first row, the sum of the probabilities of the first row should add up to 1. How about the second row? For the second row, what we know is that 80% of all the cloudy days are followed by cloudy days. So that's probability of this element. So the probability that if we are cloudy right now, what is the probability that we are cloudy in the next day as well? And that's going to be 0.8. And again, based on the condition that the sum of the probabilities of each row equals to 1, so this element of the matrix will have the probability of 0.2, meaning that if you are having a cloudy day today, the probability that tomorrow is sunny is going to be 0.2. So this is a transition probability matrix for this problem. One thing that I also want to mention before we go to the next example is that, as you can see in this example, the time step in this problem is day. So we are looking at the state of the system at each day. So it's very important for us to be able also to recognize the time step that we are using at each specific system. In the next example, we are looking at the gambling problem. So let's assume I have $2. So we are going to play a game, and in each bet, in each hand, we are going to bet $1. And at each hand, we have the probability or the chance of P to win and the chance of 1 minus P to lose. If we win at a hand, if we win with probability P, then we gain $1. If we lose with probability of 1 minus P, then we are going to lose $1. In this game, we are going to play until we earn $4 or we lose everything. We have $0. If we get to any one of these situations, we quit the game. Okay, so now we want to see how we can model this system as a stochastic system. So obviously first, read the problem statement carefully. Second, find out the characteristic of interest that you are monitoring in this system. The characteristic of interest in this system is the value of money in our hand. So then, what are the possible values for the state of the system? Or in other words, what is our state space? The possible values or the possible amounts of money that we can have in this system obviously is $0 if we lose everything, $1, $2, $3, and $4. We know that when we get to the $4, we quit, so we are not going to go to possibly $5, $6 or more. And we also know when we get to $0, we also lose everything, so we can't continue the game as well. And all these possible values between 0 to 4 are possible values or possible amount of money that we can have in our hand, and they form state of this system. Now let's put together a transition probability matrix for this problem. So as you can see, we have 5 possible states for this for this stochastic system. So when we are going to develop the transition probability matrix, it's going to be a matrix with 5 rows from state 0, 1, 2, 3, 4. State 0, 1, 2, 3, 4. So now, what is the probability of the first element here? So that means if I have $0 right now, what is the probability that in the next hand I also have $0? So this probability is going to be 1, because we said that if we reach $0, we are going to quit the game. So we are not going to ever be able to go from $0 to $1 or $2 or $3 or $4. We are going to stay at $0. Okay, so this probability is 1, and the probability of any other possible transitions from state 0 is 0. How about this element? So this is probability that if I have $1 right now, in the next hand I'm going to have $0. So this probability means that this is the probability that we lose that hand, and that happens with the probability of 1 minus P. How about this one? This means that if I have $1 right now, what is the probability that I have $1 in the next hand? So we know that's not going to happen, because at any hand we either lose or win. And so we either get to gain $1, get to the 2, or lose $1 and get to 0. How about this element? So in this one, this means the probability that if we have $1 right now, in the next hand or in the next game we have $2. So that happens if we win with probability of P. And how about going to $3? It will never happen. How about going from $1 to $4? It will never happen. Okay, how about this element? So this means that if we have $2 right now, what is the chance that in the next game we have $0? So this is not going to happen, because we cannot lose all $2 together at one hand. What is the probability that in the next hand we are going to have $1? So that happens if we lose that hand. And what is the probability that we stay with $2? Again, that's not going to happen, because at any hand we have to lose or gain. And what is the probability that we go to $3? That happens if we win that hands with probability of V. And the probability that we go from $2 to $4, it's 0. It will never happen. Then how about this one? What is the probability that if I have $3 right now, in the next hand I'll go to $0? That will never happen. What is the chance that I go to $1? That would never happen. That means you losing $2 at the same time. That is not happening, because at every hand we lose $1 or gain $1. What is the probability that I go to $2? That happens if I lose that hand with probability of 1 minus p. And what is the chance that I stay with $3? 0. What is the chance that I go to $4? That happens if I win that hand with probability of p. And how about if I have $4 at my hand? The probability that it goes to 0 is 0, 1 is 0, 2 is 0. The probability that I go to 3 is 0 as well, because we said that if we have $4 in our hands, we are going to quit. So I'm not going to continue playing so that I lose something and I go to $3. So if I have $4 in my hand with probability of 1, I'm going to stay with $4 in the next hand. So that's not going to change, and it's not going to go to any other dollar value. So this is the transition probability matrix for this problem. And as you heard, I'm repeating that the time step in this problem is each game or each hand. So at each hand or each game, we make a transition from one possible state to another possible state in this system. So now let's go to problem 3. In the third example, we are going to model the health condition of individuals. Based on the body mass index of individuals, we can put them in the normal weight category or overweight category or obese category. So at each year, we know based on the historical data that if a person is in normal weight category, there is 80% chance that the person stays in normal weight category in the next year, and there is 10% chance that the person gains weight and goes to overweight category in the next year. If a person is in overweight category, there is 70% chance that the person stays in overweight category in the next year, and there is 15% chance that the person goes to obese category in the next year. And if the person is in obese category, there is 95% chance that the person stays in obese category in the next year, and 5% chance that the person goes to overweight category in the next year. And we want to see if we can use if we can model this system as a Markov chain or as a stochastic process. So obviously, first, read the problem carefully. Second, find out the characteristic of interest that we are interested to monitor, or in other words, the state of the system. So here, the state of the system is going to be weight category. What are the possible values for the state of the system, or in other words, our state space? Those are normal weight, overweight, and obese categories. Okay, so next we want to calculate the transition probability matrix for this one. So I'm going to develop a transition probability matrix P, and this transition probability matrix is going to be 3 by 3. So now we want to put the probabilities. Okay, so what is the element that the probability that we have to put here? That means that if we are at normal weight right now, what is the probability that in the next year we also stayed in normal weight category? So as we see from the problem statement here, if we are at normal weight category, there's 85% chance that we stay as normal weight, and there's 10% chance that we go to overweight. So there is 85% chance that we stay normal weight, and there is 10% chance that we become overweight. And what is the probability that the person who is normal weight right now becomes obese in the next year? Given the fact that the sum of the probabilities of each row equals to 1, what is left here is just 5%. So 5% of people who are normal weight right now will be obese in the next year. Okay, let's complete the second row. The second row, we have to put the probability that if a person is overweight right now, what is the probability that the person becomes normal weight in the next year, stays overweight, or becomes obese? So if we go back to the problem statement, if a person is overweight, there is 75% chance that the person stays overweight, and there is 15% chance that the person becomes obese. Okay, so if a person is overweight, there is 75% chance that the person stays overweight, and there is 15% chance that the person becomes obese. Given the fact that the sum of each row equals to 1, the probability that this person who is overweight this year becomes normal weight in the next year is going to be 0.1. And how about the third row? This is the probability that if a person is obese weight category right now, what is the probability that in the next year the person is normal weight or overweight or obese category? What we have from problem statement is that if a person is obese right now in this year, with 90% chance that they stay obese in the next year, and with 5% chance they become overweight. So this means if a person is obese, with 90% chance they stay obese in the next year, and with 5% chance they become overweight, and with 5% chance they become normal weight. And again, I got this number based on the fact that the sum of the probabilities of each row equals to 1. So this becomes a transition probability matrix for this problem. And as you saw, the time step for this problem is a year, because we have the transition probabilities that happen across each year. So that becomes the time step in this problem.